From the Chapter 8 review questions at the end here of our study of polar coordinates and parametric equations, let's take a look at some of the representative questions. Students asked about number 15. Well, the directions here asked you to, first of all, convert the equation into polar coordinates, and then second of all, sketch a nice graph of it. All right, so our basic straightforward substitutions here, we should know that x squared plus y squared is r squared. We should know a substitution for x and one for y. Well, those constants, not much you can do about that, but we do know that x is equal to r cosine theta. Again, the 4 has to remain there. Y is equal to r sine theta. But if you take a look at the equations that they gave you that were in polar form and asked you to graph them for these, just about every single one of these is solved for r. You'll notice on the right-hand side, you don't see the variable r at all. Now, a couple of the more challenging, shall we say, graphs here, it's not just set equal to r, it's set equal to r squared. But the standard basically is we should have all of the r's on one side and nothing but theta on the other side. Well, I have r on both sides. So if I divide this by r, I should divide that by r, and I need to divide every term by r. R squared divided by r, that'll get me r to the first, and then I'll have 4 cosine theta plus 4 sine theta. And that seems to be pretty much as simplified as we can get. Now, if we really wanted to, I guess, we could factor out a 4 from both of the terms on the right-hand side. Not really sure how that's going to be all that helpful. So then the graph. We could take the original up here and convert that into standard form. It's a conic section. 2 squared terms, it's not a parabola. They're the same sign, it's not a hyperbola. They have the same coefficients, it's not an ellipse, that's a circle. So we could go through and graph that by, first of all, doing the completing the square method. And yeah, that's algebra 2 stuff. We could. Let's take a moment and try and graph the polar form instead. If we say put in 0 in place of theta. So let's see, cosine of 0 is 1. 4 times 1 will give you 4. The sine of 0 is 0. All right, 4 plus 0 is 4. Let's try pi over 4. For both sine and cosine, it's square root of 2 over 2. So this is 4 square root of 2 over 2 plus another 4 square root of 2 over 2, which gives me 8 square root of 2 over 2, which is really 4 square root of 2. Gonna have to do some conversion on that. So again, I'm attempting to graph this, so I want the decimal approximation. 4 times the square root of 2 will give me about 5.7. Try pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1, so I'll get 4. for pi, the cosine of pi is -1. Sine of pi is, I'm sorry, let's do 3 pi over 4 before we do pi. So 3 pi over 4 is in the second quadrant. Cosine in the second quadrant is negative, so this is going to give us 4 times negative square root of 2 over 2. But sine in the second quadrant is still positive, so this is 4 times positive square root of 2 over 2. That gives me 0. And then if I try pi, the cosine of pi is -1. The sine of pi is 0. So I get 4 times -1 plus 0. So that's -4. Well, let's see what this is starting to look like. So when my angle here is 0, I need a radius of 1, 2, 3, 4. When I'm at 5 pi over 4, I need a radius coming forward of 1, 2, 3, 4, 5.7. When my angle is pi over 2, I need a radius of 1, 2, 3, 4. For 3 pi over 4, my radius is 0. And for pi, my radius is -4. Well, that's the same exact point here. Okay. Um, yeah, I didn't do too bad there. Um, again, we know that this is the graph of a circle. Because this is 4 and this is 4. Again, cosine, you should be able to associate that with the x. Sine, you should be able to associate that with the y. It appears that it is a circle centered at, again, if we're going to go back, sorry, I'll put that up here. For our rectangular coordinates at 2, 2. Let's get a nice circle tool here. Let's see how close I can come to hitting all of those. Yeah, that seems reasonable to me. Okay, so then the process for 17 is pretty much the reverse of what we just did. So our equation here, 3 plus 3 cosine theta. We put in 0, cosine of 0 is 1, 3 times 1 is 3, 3 plus 3 is 6. We put in, say, pi over 4. Cosine of pi over 4 is square root of 2 over 2. Again, that's irrational. I'm going straight to the calculator on this one. So I need 3 plus 3 times the quantity, square root of 2 divided by 2, and just give me the decimal approximation there of about 5.1. For pi over 2, cosine is 0, 3 times 0 is 0, 3 plus 0 is 3. For 3 pi over 4, I know that cosine is negative square root of 2 over 2. So 3 minus 3 times square root of 2 over 2 will give me about 0.9. for pi, cosine is -1. Well, that means 3 minus 3, so that gives me 0. For 5 pi over 4, okay, here's where I'm going to start repeating. 3 pi over 4 and 5 pi over 4. 5 pi over 4 is in the third quadrant, cosine's negative in the third quadrant. I'm going to get the same answer that I got here for 3 pi over 4, so that's going to be 0.9. So if I do 3 pi over 2, okay, so it's going to have a horizontal line of symmetry here. So this is going to be 3, and then we'll be out to the 5.1, and of course back to 6. All right, so I need for 0 a radius of 1, 2, 3, 4, 5, 6. For pi over 4, I need a radius of about 1, 2, 3, 4, 5.1. For pi over 2, straight up 1, 2, 3 spaces. For 3 pi over 4, not quite 1. And back to my origin, and that's where things start repeating. For 5 pi over 4, not quite 1. 3 pi over 2, come forward 3 spaces. 7 pi over 4 was 1, 2, 3, 4, 5.1. And then back to 6. Again, hopefully you're familiar with the form of that. This is a cardioid. So here's my maximum distance from the pole, curves around, that sharp dent in it comes around, and again, hopefully do your best there, make it look like it has horizontal symmetry to it. Then for part B, express the equation in rectangular form. Again, we could, we're looking for r squares. We could, I don't know, square both sides. That would definitely give us an r squared on the left, but that would give us a cosine squared on the right, and yeah, I don't have a substitution for that. So instead, what I'm going to do is multiply everything by r. So on the right side, sorry, the left side, that'll give me an r squared. And I need to distribute, that gives me 3r plus 3r cosine theta. Well, again, we know a nice substitution there. We know a nice substitution here, and we're just going to have to deal with that. So r squared, again, that coefficient there stays where it is. R cosine theta is x. All right, so I guess that's progress, but I'm not quite there yet. Again, to transform this into rectangular form, I can't have any more thetas. I can't have any more r's. All right, well, I got rid of the theta, but I still need to get rid of this. Okay, so best thing to do here is to isolate that term. So that means I'm going to subtract 3x from both sides. So I'll have x squared plus y squared minus 3x is equal to 3r. Now again, I need a substitution to get rid of the r. It'd be nice if that were r squared. If I did the same thing like I did in the first part here and just again multiply both sides by r, that would give me an r squared on the right, and that would give me a mess on the left. So the other option here is square both sides. Dun dun dun. This is a huge mess. I'm going to leave it. Sorry. In its squared form. Don't see any reason to mess around that with that right now. 3r squared means 3r times 3r. So that'll give me 9r squared. And then I can make the substitution there. At this point, I say mission accomplished. I have an equation. No more r variables, no more thetas. It's just in terms of x and y, and I already have the graph. The only reason that I would expand that, get rid of the parentheses, square what's on the left, combine like terms, the only reason that I would do that is to make it easier to try and draw the graph. I already have the graph. Moving on. Number 19. Again, same directions, same process. Put in, say, 0 in place of theta. 2 times 0 is still 0. Sine of 0 is 0. 2 times 0 is 0. Yay, we're going nowhere because that's right there at the pole. Now, the fact that I'm going to have to multiply by theta, again, I want to go in small increments here. I don't want to just do those quadrant angles. 2 times pi over 4, that's pi over 2. Sine of pi over 2 is 1. 2 times 1 is 2. Pi over 2, substitute that in place of theta. Multiply it by 2, well, that's pi. Sine of pi is 0. 2 times 0 is 0. And hopefully we can, again, recognize the form there. Because we're multiplying theta by a number, because there's only one term, again, go back here before I start messing with it. We had r is equal to 2 different terms, one of them being a constant. That gave us the cardioid. Here, there's only one term, not going to be a cardioid anymore. And because we're doing a multiple of theta, this is going to give us a rose. 2, the coefficient on theta, nice even number, double that. This rose should have 4 leaves. So if I plot the point 0, 0, now I'm going to use a slightly bigger scale here, where this is 1 and this is 2. For pi over 4, I go out to 2. And then for pi over 2, I'm back to 0. That's telling me there's 1 leaf of my rose. And again, because of the symmetry that we find with these roses here, again, nice and even, we know there are 4 of them. This one here is centered on pi over 4. We should be able to figure out the rest of them there pretty easily also. So again, we'll get this pattern here. If we do just multiples of pi over 4, well, we go from 0 to 0, negative 2, 0 to 0, negative 2, 0. So the actual order that happens here when you graph this, because for 3 pi over 4, instead of coming forward 2 spaces, we have to go backward 2 spaces. We actually draw this one in first quadrant, and then this leaf gets drawn in what we, again, formerly known as the fourth quadrant. For 5 pi over 4, that's a positive 2, so we come forward 2 spaces. So that one gets drawn next. And for 7 pi over 4 down here, again, our radius is negative. So we have to go backwards. So again, it comes from here, out to there, and back, and then it starts repeating itself. All right, convert. The first thing, I don't have any kind of a substitution here for sine 2 theta. I know if I have r sine theta, that's a y, but I don't know sine 2 theta. So if we remember back to the good old first semester here, we're going to do this substitution. Sine 2 theta is equal to 2 sine theta cosine theta. Which of course gives us 4 sine theta times cosine theta. Now again, we have very limited options when it comes to substitution. We know r squared, we know r sine theta, we know r cosine theta. So if I multiply this side by r, I could multiply this side by r, but then the question is who gets it? I mean, if I put it here with this, then I can convert that into a y. If I put it here instead, then I can convert that into an x. But the question remains, what do I do with the other one? Well, why be so stingy? Multiply both of them by r. Again, keep the equation balanced. So if I'm going to multiply both of those by r's, that means here I end up with r cubed. Now that's problematic for the moment, but look at the good we did over here. R sine theta is y, r cosine theta is x. Okay, so now we've gotten rid of all of the thetas, especially that pesky 2 theta from the very start. Now we need to get rid of the r. Um, that'd be great if that were either r squared, or if we had r squared squared, r to the fourth. You know, any even multiple of r would be good. What happens here if we square both sides? And over here on the right, obviously 4 squared, that'll give us 16. The convention is in one term, again, over here on the right, that's just one term, several different components. If there are more than one variable, we put them in alphabetical order. So that's x squared, y squared. All right, now I'm going to do a little bit of magic here on the left-hand side. That r cubed squared is the same thing as saying r squared cubed. And now I can do the substitution. R squared is equal to x squared plus y squared. See previous argument. Yeah, well, gee, that'd be fun taking that x squared plus y squared, a nice binomial, cubing that out. We get x to the sixth and y to the sixth and all kinds of fun things in between. But again, the question just asked for us to convert. I really don't see any reason to mess around with that any longer. Someone else asked for number 39. So find the square roots of negative 16i. Now, Again, sometimes they write things that are incomplete. That's okay. As a complex number, this is actually 0 minus 16i. We need to find our modulus, and we need to find our argument. Well, again, if we do that tangent thing, we're going to get in trouble. Quick sketch. If we try and graph 0 minus 16i, well, again, our real component, don't move left or right. The imaginary component goes straight down. So this would be the location of 0 minus 16i, which then would give us an argument coming around here of 3 pi over 2. So we could write our complex number in polar form by saying 16 times the quantity cosine 3 pi over 2 plus I sine 3 pi over 2. So now we have it in polar form. We can apply the second half, basically, of De Moivre's theorem. And let's see, for both of our roots here, I think they call them W's. We need to take our modulus here and raise it to the 1/2 power. Well, again, raising something to the 1/2 power means taking the square root, so that's going to be 4. And then for our first argument here, we're supposed to take 3 pi over 2 and add 2 pi divided by, again, we're looking for square roots, so that means divided by 2. Well, okay, that's not too tough. I'm sorry, I'm getting a little bit ahead of myself. To find the first one, it's even easier than that. Take the original argument, and again, because it's a square root, we're going to divide by 2. So for the first root, I apologize, 3 pi over 4. To find the next one, that's where we do this. Take the previous argument and add 2 pi divided by 2. Well, okay, we need common denominators. So that's really adding 4 pi over 4. 3 pi over 4. That'll give us cosine 7 pi over 4 plus I sine 7 pi over 4. And as our previous discussions and agreements stated, if we have an argument that's a multiple of pi, if it's 5 pi, if it's 90 pi, we're going to simplify that. If it's a multiple of pi over 2, if it's 7 pi over 2, negative 98 pi over 2, whatever, we're going to simplify that. Here, your denominator is a 4. We're just going to leave it. It wouldn't be too tough, but it wouldn't be pretty either. Okay, so let's wrap up this review here by doing a little bit about parametric equations. They first of all challenge you to sketch a curve. So we're going to make a chart here, picking different values for t. Finding the corresponding values for x and y, and graphing those. Start easy. When t is equal to 0, 1 minus 0 is 1, 1 plus 0 is 1, so we'll plot the point 1, 1. Put in 1 in place of t. Well, 1 squared is 1, 1 minus 1 gives me 0, 1 plus 1 gives me 2. For 2, 2 squared is 4, 1 minus 4, that's negative 3. 1 plus 2 is positive 3. I say put in 3. 3 squared is 9. 1 minus 9 will give me negative 8. 1 plus 3 is 4. Well, now if I stop for a moment here and look at what's going on with my x's, it went from positive to 0 to negative to more negative. I imagine, yeah, okay, I can anticipate this. If I put in 4, I'm going to get negative 15 here. How about I put in a few negative values for t and see what happens? But if I take negative 1 and square it, that's positive 1. 1 minus 1 is 0. Now here for my y coordinate, it's going to matter. 1 minus 1. Okay, so I get the origin there. I get the point 0, 0. Put in negative 2 in place of t. Negative 2 squared is 4. 1 minus 4 gives me negative 3. But for my y, 1 minus 2, that's negative 1. If I put in negative 3 in place of t, that's 1 minus 9. That'll give me, well, negative 8 again. But my y is now 1 plus negative 3. That's negative 2. All right, I think that might be enough to get an idea of the shape of the graph. So if I plot the point 1, 1, I plot the point 0, 2, negative 3, positive 3, negative 8, positive 4. Well, it's definitely not a line here. I need to also include the point 0, 0, negative 3, negative 1, and negative 8, negative 2. Yeah, it looks like we have ourselves a lovely little parabola here, opening to the left. Now remember, for a parametric graph, we not only have to calculate, we've got to plot the points, we've got to connect the dots. Again, I'm making it easy on myself, picking nothing but integers there for t. The other property here, the other component that you need to include is arrows indicating direction. So if I'm going from t is negative values that were down here, goes through 0, 0, and then turns. As my values for t are positive, it goes in this direction. So again, we could look at this as a way of describing the path of an object at different points in time. Okay, so your parametric graph has to have some arrows on it. Don't forget that. All right, then the last part here, find the simpler equation. All right, so hopefully you're seeing what I'm seeing here. And oh my goodness, this is going to be so much easier to deal with. So if I simply subtract 1 from both sides, I'll have t is equal to y minus 1. Substitute that into the first one. X is equal to 1 minus t squared, so that's y minus 1 squared. Now in this case, I'm going to take this a little bit further because I have a constant outside the parentheses, I have a constant inside the parentheses. So if I take y minus 1 and square that, again, please do the FOIL method. That should give me y squared minus 2y plus 1. But again, it's 1 minus this, so I'm just going to basically treat that as a negative 1 and distribute. So it's 1 minus y squared plus 2y minus 1, and hey, would you look at that, the positive and the negative there. simplify this down even further, whoops, sorry. No, that was not some sort of algebra substitution. I just forgot to write it down. Sorry. Um, yeah, so there's a single equation with x and y. I've eliminated the parameter t. Now, if we, again, for a moment here, understand because of the graph, see that already, this is not a function, so I don't need to take that final equation there and solve it for y. I've already got the graph. I don't need to put that into a calculator and try and get the graph that way. But if we, say, modify those questions about conic sections, we have one squared term and only one squared term, not a circle, not an ellipse, not a hyperbola. This is a parabola. It's y squared, so it either opens left or right. It's negative y squared, so we know it opens to the left. And that's exactly what we see with the graph already. All right, I hope that was helpful. I hope that wasn't too long. God bless you all. Hopefully, I'll see everybody back in class soon, nice and healthy.